Thank you. All right, hello y'all. This is episode 2 of my Here Type Check Deep Dive series. I'm going to be vaguely talking about coercion. So some of the data structures that we use internally in the compiler to perform coercion, what coercion is, and running through some of the methods that the types of coercions that we implement and how they're implemented and like why they're like that, because some of the different kinds of coercions that we implement in the compiler are a little weird, and this is not for, it's not for no good reason. It's because that we have pretty subtle behaviors that we want to implement, both for kind of backwards compatibility reasons and just general, this is how it was implemented, and we like the way that it behaves in certain kind of corner cases of the type checker. So top level though, coercion is a type of it's a type of operation that can happen at certain points in your program. It's different than subtyping. A lot of people get coercion and subtyping mixed up because what other languages call subtyping or actually treat as subtyping, Rust treats as coercion instead. So in Rust, subtyping is specifically a relationship between types that are really, up to modulo regions or lifetimes. So for example, if y'all can see my screen, like this is a subtyping that happens in Rust. So this expression right here has the type static stir, and we're assigning it to a variable that has some other lifetime that we're inferencing stir. And here tick static stir, a reference to tick static stir is a subtype of a reference of any other kind of stir with any lifetime. However, for example, if we were doing something like new this is not subtyping. Is taking something as a type of box of string and unsizing it. So unsizing is a type of coercion that takes a sized type like box of string and turns into an unsized type, or takes a size type like string and turns into an unsized type like din trait. That's not subtyping. That's coercion, as I was saying before. And the way that we perform subtyping and coercion is pretty different. I won't go into too much detail of how we perform subtyping in the compiler, but maybe some other time. But yeah, so the way we perform coercion, well, two things, I guess. One is that coercion only happens in here type check. It doesn't happen implicitly during trait selection or during any other kind of points where we're taking types and trying to smush them together in the compiler. It really only happens during here type check. And after here type check, we record the types of coercions that we do as something called adjustments. They're kind of implicit operations that occur that are inferred during the type checking process. And then we elaborate those adjustments into explicit operations when we're building mirror, for example. And after mirror has been built, all the coercions are treated basically just as explicit casts of different kinds, depending on the coercion that we inferred. So because coercion only happens during here type check, we implement them kind of, they don't need to be as they're not as rigid as, for example, like orphan checks or coherence checks or anything like that. They are pretty much best effort. If we can't tell what types we're trying to coerce something into, we just fall back to just subtyping the types, and it will lead to subtle but interesting type errors, for example, sometimes in your code. Understanding how coercion happens will help understand why these subtyping or why these type inequality errors occur, and also probably why we can't fix them. I think a lot of bugs get filed, and sometimes you just have to say, sorry, this is not fixable, because fixing it would require changing the heuristical behavior of coercions, and that causes other code to break, and we have to keep code that compiling with, unless we want to go through the whole process of future compatibility errors and possibly lots of discussions between lang team and types team and stuff like that. So before I dive into the code, does anyone have any questions? It's kind of a rambly rant, but I hope I got y'all kind of in the right mindset for talking about this coercion code. No. Okay, well, if people do have questions, then leave them in the chat, and I will read them. I just pulled up the chat and I saw that Eric asked a question about, are we focusing on coercion today? Yes, we are. So, right. So coercion is mostly located in a single file in Rustc here typecheck called coercion.rs, surprising. And it's broken up into two different main data structures. The first is called coerce, and it's essentially just a helper. It's a wrapper around some state flags that we would have to pass around to all the kind of the coercion subroutines. So as I said before, there are different kinds of coercions, and those are broken up into different functions. So instead of passing these three inputs to every single coercion subroutine, basically, that we enter in through a top level coerce function. If I can find it, coerce. Yeah, so we enter in through this top level coerce function. If we didn't have this coerce wrapper, then we would have to also pass in the cause. I'd have to pass in this Boolean that says whether we're using the least upper bound coercion strategy or not, and then this two-phase borrow flag. So this coercion data structure is essentially just kind of a please add a little bit more context onto our usual type checking module called function context that has all the other stuff that we usually need during type checking. But yeah, so we we create a coercion thing at some coercion point by constructing this, and this is essentially just a wrapper around the struct constructor. Then we enter into the coerce method, which is kind of the start of our coercion behavior. Now, before I guess maybe before I jump into this, this is used for coercing one type into the other. So this is specifically for coercions that happen at places like struct construction. So if we have a struct that looks like this, and we construct this is a coercion because we take the field X and we use the field X's type to tell that we need to take this box, which is not a box of din display, and coerce into a box of din display. And we use this coercion data structure in the compiler to do that. There's other kinds of coercions, specifically one that looks like an if else. This is kind of I'll call it multi-arm coercion. And this uses a different data structure that I'm going to jump into after kind of lightly covering the kinds of coercions that we have in the compiler. This is actually handled by a different data structure that is also in this file called coerce. So coerce many is used to handle the case where we're trying to take a bunch of different things and coerce them all into one tie. And luckily, this is just a data structure that wraps even more information, some state information about the types that we're coercing and the expressions that we're using to coerce into. But it actually just wraps the coerce data structure that we're going to jump into. So that was a little aside. Let's jump back into the course. This one, right? So all the coercion methods have the kind of the concept of like a original type and a target type. The type that we're coercing from and the type that we're targeting to coerce into. Helpfully, though, all this coercion code just calls them A and B. Just know that A is the thing that is being coerced, and B is the thing that's being coerced into, or the target. If anyone wants to go through this code and rename it, that might be helpful. Though again, it's just naming, and you kind of realize after reading the code for a bit that A is the one that's being coerced from, and B is the one that's being coerced into. The first interesting coercion that we have is just the never coercion. So the type never, the bang type, the unreachable type, or whatever you want to call it, diverging type, is allowed to be coerced into anything. So before we go into any interesting kind of coercion, if we have a never type on the left-hand side, which is the thing that's being coerced from, we just immediately bail. We store one adjustment, which is that never can be coerced into anything, and we just bail out of it. We don't try doing any other kind of coercions because they would be made redundant by this one that just handles every case of coercion. Secondly, if we don't know anything about the type we're coercing from, that is, if the left-hand side of the coercion is an inference variable, then we just bail. We don't try to do any coercion, because all of the coercion that we do in the compiler is like fully structural. So it depends on us knowing something about the left-hand side of the type. So if we need to know that the type is we need to know that the type is like an inference variable, or sorry, not like an ADT, or an array, or something like that, to actually know what kinds of coercions is supported by that type. So if it's an inference variable, we fall back to coerce from inference variable, and all that does is just well, it creates a coercion predicate and registers that into the trait engine that we have, the trait solver that we have for our type checker. But the coerce predicate doesn't do anything right now. It just falls back to subtyping. It's just that we can't actually subtype the types until we know what they are. So we register as a goal, and as soon as we find out what the types are, as soon as we do some inference, then that goal get processed by the type, or by the trait solver, and it'll cause us to make subtyping inference progress. But this doesn't do anything interesting. So if you have an inference variable, and then we eventually constrain that inference variable to be something that can be coerced into, that does us no good, essentially. So for example, let me see if I can create an example that illuminates this. Let's see. We don't know what it is. This is obviously redundant, but I'm just making it explicit. 2, 3. So this is technically a coercion point, but we're trying to coerce basically an array of I32.3 into something, and then later on we infer that X is actually a slice. So let's see, what's the best way of doing this? I can just EQ using this function called EQ that constrains a type. So you can turbofish a type that you want to constrain its value to. So we're saying that this is an I32, and actually this will work because I think this will work because this is also a coercion point. An argument to a function also allows coercion, so this will just work, I think. Yes, this works, unfortunately. Let's see, what are any good ways to make this work? Um, Nothing comes to mind right now. But just know, I guess, that if we don't have any inference, oh, I guess I can create kind of an annoying example. So let's see. Closure. I think it's an error. I don't know if it's an error, but I think it's just aha. So this is this is an error that has to do with the fact that we don't know what the return type of the closure is supposed to be. So if I elaborate this, this code looks like this, for example. We don't know what the return type of the closure is supposed to be, even though a closure return is a coercion site. This unfortunately doesn't give us enough information to do coercion, so we fall back to just subtyping this. So we infer that this closure returns just box of I32. Then when we require that closure to actually be a closure that returns a return type of box of DIN display, it turns out that that closure doesn't actually return the right type. If I were to provide type descriptions, and I think it works. Yes, it does work, because as I said before, the return type of a closure is a coercion point. It's just that we didn't have enough type information to actually do anything useful during coercion, if that makes sense. And that is essentially what's being handled at this fallback, is basically if we don't know what the coercion, what the right hand side, the kind of the target of the coercion is supposed to be, then we can't actually do anything. We fall back to subtyping. So that's an aside, is that coercion is very type specific. It requires us to actually know what the type, the kind of the type is. So is it an array? Is it a slice? Is it a box? Is it a, an ADT? We need to know that information to actually be able to perform any useful coercion. Without that, we can't do anything and we just bail. We fall back to something that always works technically, but it might not give us the right types later on in the program. I'll run through this function first before diving into coercion sized. So one of the most important kinds of coercion that we can do is unsizing. It takes a type that has a subtype somewhere in it, like a box of T, and turns it into something that that is an unsized type. So it turns like a box of T into a box of DIN trait, for example, or it takes a reference to a array and turns it into a reference of a slice. And the way it does that is pretty interesting, but I will not go into it yet because that will require a lot of background knowledge, and I'll jump into the different traits that we use to support it. So then, as I said before, coercion relies on us knowing what kinds of types we're coercing to and from. So we actually just match on the tie kind of the target. And if it's a pointer, then we coerce unsafe pointers, which does coercion between different kinds of pointer kinds, raw pointer kinds. So I think I'm pretty sure it allows us to coerce something like like something that has the type of like a mutable raw pointer into a const raw pointer, or I guess, or also like a regular ref into a raw pointer. That's what coerce mutables is doing. It takes something that is possibly, it takes things that are either mutable or immutable and allows you to coerce into something that's immutable. Let's see. It also handles, it handles coercing via refs. So to take a ref and coerce it into a raw pointer is actually just like a deref and then a borrow again. So that's how we desugar coercing a ref into a raw pointer. Otherwise, we adjust mutable raw pointers into const raw pointers, and then we make sure that the types are compatible. So same thing with borrow pointers. You have the same behavior where we can take like a mutable ref to something and turn it into an immutable ref to something that also requires reborrowing the mutable pointer, so we don't have to borrow it for the whole lifetime of the mutable pointer. And we do some subtyping there and stuff like that. We also allow coercing from a pointer sized type into something called a din star. So din star types are sized din trait objects, and those allow they're an experimental feature that's used to kind of play around with some async function coercion that we want to eventually handle in the future, or async function and trait coercion that we want to eventually handle in the future. The way that sorry, my Outlook is being loud and annoying. Give me a second, I need to kill that. Oh my gosh, close. 1 second. Okay, Outlook is vanquished. So the way that we handle coercing a type into a din star, it's handled slightly the same way as we do unsized coercion above, but we don't go through the same unsized traits that we do with unsized coercion, because din star doesn't allow the same kind of structural unsizing that unsized coercion does. I won't jump into it just because the code is pretty straightforward. And then we have some coercions that are based off of the thing that we're coercing from. So an fndef is the ZST that is specific to every function item that we have in the program, and we allow coercing fndefs into function pointers, which is handled by coerce from fn item. We allow fn pointers to, as the comment says, dropping their unsafe qualifiers. So we can coerce from a safe function into an unsafe function, I'm pretty sure. Let's see. So yeah, so we can, every safe function is technically an unsafe function. It's just an unsafe function that has trivial safety requirements. So we allow coercing from a safe function to an unsafe function. The way that we word this function is a little backwards. But anyways, and then we finally allow coercing closures to function pointers if the closure doesn't capture anything. So if a closure doesn't capture anything, then we can think of that closure as just a anonymous function that that participates in the same inference as the body of the function that we're type checking, which is sometimes useful. It's sometimes useful to not have to write out for example, the argument and return types of a function, even though the closure didn't capture anything from the body. We can then coerce it into a function pointer, which is then used somewhere else. Function pointers are they're sized and they're concrete, so they're more powerful than, for example, just a generic that implements the function traits. So sometimes it's useful to coerce a function pointer or closure to a function pointer. And then if we have no other kind of coercion that allows us to do anything productive, we just fall back to unification. So this is just the subtyping that I was talking about earlier. Again, this is always something that we can do. It's just not always the best choice for what to do, because it sometimes leads to not the best inference behavior later on. So I guess before I jump into unsized coercion, does anyone have any questions? Does anyone want me to go into kind of the nitty-gritty of any of these specific functions that I kind of glossed over. They are really just bookkeeping, but I will, I can run through them if people want.
How are polymorphic function definitions coerced to function pointers? Is there any special handling, or is it automatic?
It is automatic. So that is interesting. I guess maybe we can jump into how we coerce f and defs to function signatures. So essentially it's free because we use subtyping. It's just the fact is we need to extract the function signature from the function point, like the f and def type, and then as soon as we do subtyping with those function signatures, it just kind of works. But yeah, we can look through this right now. So first we normalize the B tie. I don't exactly know why we do this, but we do. I have absolutely no idea actually why this normalization call is here. We should be normalizing earlier, but we do. So if the A tie, so the A tie is understood to be a function in f and def. If the B tie is a function pointer, then we extract the function signature from both. Well, we have the function signature from the B tie. We extract the function signature from the A tie, and then we equate them somewhere around here. Oh, right at the end of this line. Yeah, so coerce from safeFN. So coerce from safeFN just equates the two types, or not equates them, but subtypes the two types. So it allows basically or higher ranked function pointers are subtypes of other higher ranked function pointer types, depending on how the late bound vars work out. So we just subtype the two types to make sure that the function signatures are compatible. So we're not trying to coerce from a function that like takes an I32 argument into something that takes a U32 argument. But yeah, so it's all just special subtyping. The way we do it actually, we take the I think we take the function signature and turn it back into a function pointer somewhere. Yes, we do. It's not necessary necessarily, but we do use it for some bookkeeping. This could just be a function signature, for example. So yeah, and then we just store two different adjustments. So reify fn pointer takes an fn item and turns into an fn pointer, and then we then possibly, if we're turning an unsafe function or a safe function to an unsafe function, then we store that as well in mirror. I hope that answered your question. So cool. And then I guess just to kind of close the loop, coerce from safeFN, just all it does is call unify and, which just use sub or LUB. So LUB and subbing, it just takes two types and tries to smush them together using subtyping rules, not coercion rules. So right, so let's go back up jump back up the stack, coercion method pointer. Right. So the most interesting subtyping coercion, in my opinion, is unsized coercion. So again, as we can see from this comment, and this is actually wrong. As we can see from this comment, there's the main kinds of subtyping coercions are taking slices or taking arrays and turning them into slices, taking concrete types and turning them to DIN traits. Those are, as far as I'm aware, the only big ones. The way that those are handled are through two library traits. One's called unsize, and I will find that. One's called unsize, and it's basically, it's a built-in type that cannot be implemented specifically by any user. So Rustc deny explicit impl is a built-in attribute that we use in the standard library to say that users cannot implement this trait themselves. And if they do, then get an error, and it'll throw an error that says this is a built-in trait, don't implement it yourself. And it handles the unsizing rules for arrays into slices, types that implement trait into DIN trait, and then it handles also turning a struct into an unsized struct if the last field of that struct is unsizable. And also the same thing with tuples. I don't even know if this talks about tuples. Structs? No, it does not talk about tuples. I'm going to leave a comment. Tuples also are allowed to be unsized if the last field in the tuple can be unsized. And it's currently gated behind a feature branch, but this is a built-in trait and it's also gated behind a feature branch. So I think we should at least discuss that. And it's also used alongside the coercion sized trait, which is the user implementable trait that says, I want my smart pointer to participate in unsizing. So coercion unsize is implemented by things like box and arc and RC to allow unsizing the thing that's being pointed to. It is different than the unsize rule for structs, because the unsize rule for structs has to do with the last field in the struct being unsized. This has to do with the thing that is being pointed to by the smart pointer being unsized, and it has slightly different rules. Specifically, any field can be unsized for a coercion sized implementation. More than one field can be unsized, and it really just has to do with the generic arguments of the struct that's being unsized. I don't think I'll go into too much detail about the rules about when something is allowed to implement coercion size, because I think the Nomicon actually has a pretty thorough discussion about how that's allowed. And honestly, really, if anyone wants to understand how coercion size works, you should really just write your own smart pointer and try to implement coercion size yourself, because the compiler errors that the compiler will give you when you're not implementing it correctly are actually pretty helpful, as far as I can recall. And if they're not helpful, file a bug, I'll fix it. So these are the two traits that power coercion. And using these traits means that we don't have to have so many built-in rules and match statements and kind of exhaustive matches on the types of coercions we can allow, because when things run through the trait system, that means they can be expressed as impls in the standard library, which means that then kind of moves code out of the compiler and into the standard library, which is always nice. Does anyone have any questions about these two traits before I jump into the kind of the main coercion loop of unsized course? Nope. All right. So again, if I don't even know why we have these. If these tyvar checks, we already did check if the source is a tyvar earlier. But again, we can't apply coercions if we don't actually know the things that we're coercing from and to. So if we have tyvars as either the right or left or right hand side of the coercion, then we just bail. Again, if we also don't have built-in implementation, or if we don't have built-in definitions for unsize and coercion size, then we also bail. This should never happen unless you're using no core. And this is just to make sure that we don't ice later on by trying to look for these definitions. We want to be able to fall back somewhat gracefully if unsize or coercion size are not provided by the standard library, because unlike the sized trait, for example, typecheck doesn't really need unsize and coercion size. It's just things just act a little bit weirder if we don't have those traits. But for things like code gen backends that use mini versions of core to do unit tests, we don't want them to have to provide every single implementation of every single built-in trait in the standard library. So we fall back gracefully and we just say we cannot coerce if we don't have these types. Then we have special rules for reborrowing the source and target traits, specifically for coercion. So we do have built-in coerce. We do have coercion-sized implementations for the built-in pointer types. So let's see. Where is we do have built-in coercion-sized implementations for the pointer types. But as you can see from this implementation, they require the the source and target types to have the same lifetime. And sometimes we want to pair together both a reborrow, which shortens the lifetime of, for example, mutable pointer. And oh, actually, are these the same? Oh no. Yeah, sometimes we want to pair both a reborrow together with a coercion size. So we just manually handle the reborrowing case up in the coercion loop. I'm actually surprised and somewhat confused why we don't do the same thing that we do right here, which is the coercion from a mutable pointer to an unsized immutable pointer, which does allow us to shorten the lifetime of the target. So maybe I will spend some time after this looking at that. But again, if we have two references, then we reborrow it here, which just allows us to have kind of more relaxed lifetime rules, and it just leads to better ergonomics generally. Then we jump into the loop of coercion. So we create a new type variable and we unify the target that we have with that type variable. I think what this does is essentially I actually don't know what this does. I think it generalizes the type variables of the thing that we're unsizing. So generalization is for example, taking a type like, like static t and turning it into a pick underscore t. And this, I think, also has to do with some of this reborrowing logic that's happening up here. So set up either a subtyping or a lub coercion between the coercion size target and the expected type. And this, again, just makes sure that we are not constraining types too much when we're trying to unsize the type in coercion, I'm pretty sure. The way to find out what this is doing and why would be to remove this type variable here and see what happens. And what's probably going to happen is you'll get a bunch of type outlives, pointer must outlive this, but it's dropped at the end of the block type, or dropped at the end of the expression type errors. But again, this is just to make sure that lifetime things work correctly here. This also might be redundant now that we don't have lifetime type checking in here type check. But again, needs experimentation. Need some testing and seeing what happens when you drop it, and see what UI tests break. Anyways, then we get into the actual meat of the unsizing logic. So we set up this FIFO queue for what this calls as a custom fulfillment procedure. And what this does is essentially we start out with one obligation, which is that the source implements coercion sized, where the generic type of the coercion sized trait is the target. And then in a loop, while that queue is empty, we pop off of that queue and we select that trait obligation. So selection basically performs one step of trait selection. So what it does is it tells us whether or not something is implemented, and if it is implemented, what are the nested where clauses that are required to be upheld in order for that impl, for example, to hold. So I'm going to jump to the good case here. So if we know what the implementation source is, so if we find an impl that satisfies this coercion sized goal, then we extend the queue with the nested obligations of that source. And if that built-in impl source is a trait upcasting goal or a tuple unsizing goal, then just record some information so we can make sure that we enforce that we have the right feature gates enabled. So because some built-in coercions are still unstable, we have to basically make sure that we're enforcing that those unstable feature flags are actually active. Once trade upcasting is stabilized, we'll be able to remove this. And once tuple unsizing is either stabilized or removed, we'll also be able to remove this. And this code will be very simple. It'll just be return the nested obligations of the nested obligations of the one level of trait selection that we've done. And then we loop. If it's an error, then we report a selection error. We basically just say that the coercion was unsuccessful, and and we just bail with an error. I'm pretty sure. Actually, we continue to loop. I guess the reason that I'm guessing the reason that we don't just break this outer loop right here is to give kind of more in-depth, more errors. If there's several errors that both fail for different reasons, it may be useful to report both of them. But for correctness purposes, we could just bail right here. So I might also look into this. Anyways, this is for, oh, right, again, this is also for object safety violations and other non-unimplemented errors. If coercion size just isn't implemented, then we just treat the coercion as not being possible. So for example, if we're trying to coerce two different smart pointers that don't implement coercion size, like manual smart pointers that you implement in stable non-nightly Rust, then of course coercion size is not implemented because there's no implementation for it, and we just bail and we fall back and we try other kinds of coercions that we talked about earlier. And then finally, if we return OK of none from selection, OK of none is kind of a poorly named, it's a poorly named kind of, I don't really like the fact that it's wrapped in two different variants, but it is like that because I tried to change it once and there was a perf regression. But it's essentially, it means that we don't know. We either don't know what provides the implementation of this coercion size goal or unsized trait goal, or we don't know for certain whether or not it holds, or we don't know certainly enough to be able to make progress on it. And we have to handle that in specific ways because we don't get a list of nested obligations back because we didn't actually do any selection. We need to handle this in kind of subtle ways. If it is an unsized trait, so if it has to do with the unsized trait, which is the built-in rules for unsizing, then we have one special case. Which is if we're trying to unsize from a type variable to a din trait, and we know that that type variable is sized, then we can continue with the coercion. Otherwise, if we don't know whether or not something implements the unsized goal, then we bail with a mismatch. And if we have ambiguity in a trait that is not the unsized trait, then we also just bail with a mismatch. And that provides, I guess, maybe I can give an example of where we would possibly want this specific hack to succeed. For example, and I think I know off the top of my head how this can succeed. So X is for example, but actually we don't even need that. We could just provide one here. This code actually, I think, no. It's not completely correct. Is it? Hold up. Let me look at this code specifically. No, it has to do with type R specifically. Right, so and so I need to move this into a different pretty sure this works. Let's see if I'm correct. Oh, right. I need to. Constrain this, I think. Let's see. No, this is not right. When does this hold? I guess to explain my thinking, I thought that this would cause us to get into a situation where we have some box of some type variable. We don't actually know what that type variable is, but through virtue of calling box on something, the box new constructor requires that the type variable is sized. Where's it's sized, which then means that when we try to coerce box of something into box of the display, that registers equals course unsized box of zeros, course unsized display, which then has a nested obligation, which is zeros inside. So display, which is ambiguous. But because it's ambiguous, but this is a type bar that is sized, because we know it's sized because of the nested obligation from the box constructor, this should work. I don't know why it doesn't work, actually. Strange. Self-type. Yeah, that is strange. Anyways, then I might give me a second. I need to think about when this actually when it actually matters. Because certainly things rely on this behavior. But I don't know what. Am I getting something wrong here? It might be that and actually no. Anyways, I mean, we could make this manual and see what happens if I just see what breaks when I just do that. I think I have. This is going to take a while. Anyways, right. While we're waiting for the Rust compiler to build, does anyone have any questions? Nope.
I had a question.
Oh, yes.
This is actually from earlier when we started. In the course function, there was in the main one, there were coercions based on the target type and some based on the source type. And I didn't catch what are the guidelines for that? Like why is some done one way and some done the other?
Totally ad hoc. Absolutely, completely ad hoc. It's just that I think it just has to do with the organization of the code. Is that some coercions really do rely on us knowing what either the source or the target type are. For example, if we have a source type that is a closure, it doesn't really matter what the target type is. The only things we can really do with that closure are turn them into a function pointer if they don't capture anything. And then conversely, if we, for example, know that, actually, let me come up with an example with the target type. Let's see. A little bit. I hope this isn't too small. Let's see, B tie. Let's match on B tie. Right. So then if the target type is like a raw pointer or a ref or something like that, the thing that we want to do typically is coerce it from a different kind of pointer type. So these could actually, I mean, technically, these could be completely exhaustive. We could match on both A tie and B tie and just have like an exhaustive list of all the different kinds of coercions that we could support. It's just that like kind of think of these as think of these two matches as like one match just with a bunch of like underscores to be like, I don't really care what the left or right hand side are. And it's just kind of, it's just very heavily elided with all the different combinations just kind of like implicitly overlapping each other. So no, there are no guidelines. It's totally ad hoc. A lot of this coercion code was written somewhat long time ago, and it's just been kind of adjusted over the years. If someone actually wanted to sit down and make these lists more kind of thoroughly kind of clear what kinds of left and right hand types they support, it might actually simplify some of the kind of the inner ties, because what happens is sometimes, for example, we match on B tie. For example, we match on B tie, the target type when we're trying to coerce a ref, and then inside of the function where we try to coerce a ref, we then match on A tie again. So it's not like we're not matching on the source. It's just like we're doing it in kind of depending on what order it's happening. So that is an answer to your question.
Yeah, no, that makes total sense. Thanks.
Again, it's just kind of all over the place, this coercion code. Mostly why going through it and running through it and talking about it is the best way of understanding it, just because it's not like there's just like one mega coercion match statement that you can consult for whether or not a coercion is supported by the compiler. Sometimes you have to kind of understand it by running through it and seeing what it would do if you give it different input types. Yeah. So here's a test that fails. It has to do with fallback, I think, or never coercion. Let's see. Interesting. Weird. I'm pretty sure. I think it's this one is the one that's failing. Let's see. Enable the never type and also import error. Right. Okay. That's so strange. Because that is exactly what I I tried to do here. They both should have sized obligations being registered for it. Right. So without fallback, and without, let's see. Strange. I have a vague understanding why this is failing, but I also don't understand why the example that I made earlier does not, or actually does cause us to constrain the type to identity. Guess we can look at the issue. I'm gonna look at the issue real quick. Size. Anyways, I digress. So right, this box constructor requires us to say that X, which we don't know the type of, because the never type coerces into everything. So this ends up coercing into an unknown type. this box constructor requires us to, it constrains this type variable to be sized. That's the only thing we know about it, is that it's sized. And then if we're trying to coerce that into a box of tin error, then we need to be able to make progress on that coercion, even though we have a type variable on the left-hand side. That's a hack. I really don't like that. And also, given the fact that it only causes one test to fail, suggests to me that it's not a super important hack either. But who knows? I guess we'd have to see the creator run of removing it. But again, that's just the one kind of weird quirk of unsized coercion, is that we usually bail during coercion if we have ambiguity. And if we have ambiguity, we just totally bail unless we have this special case where we have a type variable and the type variable size is known to be sized. Anyways. Okay. I thought this was more load bearing than it actually was. So TIL. Anyways, that's all of unsized coercion. Does anyone have any questions about this loop specifically? Nope. Anyways, okay, so that I think covers all of the different kinds of tie-to-tie coercions. I said before that I was going to cover one different kind of coercion, which is the multiple arms into one kind of coercion. So this is the type of coercion strategy that we use when we have like a match statement with a bunch of different arms, or an if-else. This can be seen as two different arms that are both coerced into kind of a common type that is returned by the if. This is also what we use to support return statements, because you can think of a function as kind of a bunch of different arms. Every single arm is every explicit return statement in the program, plus one arm for the return, like the implicit return type of the function, if that explicit return type is actually covered, if that explicit return type is actually reachable. So if you have a return statement as like the last statement in a block, we don't treat that block as implicitly returning anything. And so this is handled by coerce many. And coerce many is, again, if you want to understand it the best, then you can also read the comment on it, but it's essentially said what I'm talking about. It handles a case of wanting to coerce a bunch of different things, a bunch of different expressions specifically into one. The way it happens is by repeatedly calling coerce on this coerce many structure. So you make a new coerce many and you pass in an expectation. The expectation is the same expectation I was talking about last week, which it's just the kind of the type information that's being bubbled up from the thing that is being typed, like the outer expression that's being type checked. So we started out, we basically precede it with an expected tie, and then you repeatedly call coerce on it with different expressions. So every arm of a match, for example, gets called coerce on it, and you give it expression tie, and it will basically try to fudge together the expectation tie and the tie that you pass in into kind of a common type that it will keep record of. And every single time you coerce something new into it, it'll try to find something that kind of fudges those two types together. And the way that happens is some error handling and type variable handling. So we pass in an expression, and if it's the first expression we have, we just use a regular try coerce. That's the coercion that we just talked about, the two-type coercion. We try to coerce the expression tie into the expectation tie that we passed in. There's a comment here that says something about not understanding why we do this. This is wrong. If you delete this whole branch, then it does cause a lot of reborrowing issues and stuff like that. So this, I might spend some time updating this comment to explain exactly why it's useful to first start out by trying to coerce the first type you pass in with the expectation that gets passed into the coerce many, and then basically for every subsequent arm of the match, for example, we then call try find coercion LUB, which is basically like a special cased try coerce function. It handles one special case that is not as gracefully handled in the original, like the two type coercion code that we were talking about earlier. And this is the coercing function pointer, coercing closures and function pointers into or coercing closures into function pointers if they don't capture anything. So there's some kind of subtle destructuring code happening here about trying to find the LUB or least upper bound between a closure and a function pointer, and this is essentially to handle the case because we don't support coercing function pointers into closures. So like in the other direction. So if you have a match arm, I think if you have a match arm that that first has a closure and then has a function pointer after that, if we fall back to just using the try coerce function that we were discussing earlier, then it would say I can't coerce a function pointer into closure. So this specifically has to handle the coercion in the other direction, in the direction that we don't really think about when we're talking about two type coercion, basically like source and then expected. This somewhat verbosely repeats a lot of the logic that we have in the try coerce closure, I think it's what it's called, code, but alas, it works. So that's that. So if we don't do this kind of signature based closure coercion and early return here, then we just fall back into using the regular coerce machinery, and then we do some kind of coerce many specific error reporting here, and that's really it as far as I'm aware. Is we do some error reporting, but otherwise we're just using the two-step or the two type coercion code for coerce many, and then what we do is we then take that we take the type that we get out of that coercion, I'm pretty sure, and store it as our new kind of combined merged type is what it's called. It's the type that is the type that is merged from all the different arms, I'm pretty sure, is where we store it here. Result, yeah, so we get it as a return type from this result, and then we store it into, where do we store merged type? Do we store merge type? Am I wrong? I don't store merge type. Final tie. We store final tie, I think. Right. Okay. Yeah. So we store. I was just looking for the wrong word. We store the final tie here, as the result of our coercion LUP. Right. So that's coerce many. It stores it has to store all the different expressions that have been passed into it before. Depending on the type of coercion that we're doing, we might know all the different expressions that we're coercing up front. So like a match, it has a fixed number of match arms, for example. We can pre-populate it with the list of those expressions kind of from the beginning. And this is just an efficiency thing. So we don't have to continue kind of pushing things onto a vector. However, for coercion, like all the return expressions in a body, we don't actually have that gathered into a vector somewhere. We would have to walk through the body of of a function to actually gather all those. So it's just easier to store like a running list of all the all the expressions that we've coerced currently. We use these expressions during error reporting. It's what gives you those nice errors like expected because of this previous match arm, but now I found this type because of this match arm or something like that. I don't think it is used anywhere on the good path, but we do need to record it for the bad path. Any questions about coerce many?
Is the order that they're processed significant in terms of what's accepted?
It should not be. It should not be because of the only thing that would be order specific is that special logic that I was talking about with coercing a closure into a function pointer. So I could believe if we had a code that looked like this, whatever it is, closure, and then we have something else, which is, I don't know, another function that has no signature with the name. If we just used a naive strategy, which is we start out with the expectation. In this case, the expectation is nothing. And then we try to coerce our next type into that coercion. So we try to coerce closure into nothing, because nothing has no type information. We just equate this nothing variable into closure. So this would like set with the closure. And then we go to the next arm where we have some function and we try to coerce that into the value of our merge type, which is at this point closure. Then this would be an error, if that makes sense. But as far as I'm aware, the only case where that matters is probably is possibly coercion with closures. It's possible that this is also a problem with unsized coercions. Actually, that's a good question. Let's see. This might cause an error. Oh, no, it doesn't. Interesting. Let's try this another way without interruption. No. So no, I guess to answer your question, no, the code is designed to not be order dependent, because what we want to do is we want to take the common, kind of the least upper bound, the coercion, the thing we want to essentially deduce is the type that everything else can be coerced into. Again, that is heuristical because we need to at least have enough type information to be able to find that out. But no, it is not order dependent as far as I'm aware.
Yeah, so type variables, they get freshened in the least upper bound check, or
yeah. So we use so we set this use lub flag not in course, but in course many here. Yeah, so in course many, again, so for all the types that aren't just the first, or sorry, for all the arms that are not just the first arm, we set this use LUB flag here, and then that use LUB flag is used by coerce to use when we try to unify two types, which is, this is not coercion, this is actually, this is subtyping, this is using the typing lattice. If you use LUB as set to true, then we use the LUB relation, which tries to, which it doesn't actually like freshen all the type variables that are being mentioned in the arms of the match, but it will try to, it'll do a bit more work to try to find something that is actually the LUB between all the types, for example. So it should handle the case where like you need to reborrow one of the arms because the other arm is a lifetime that's shorter than than the one that is being mentioned. So I think I'm pretty sure this is kind of where I need to go remind myself of how this works. So I might be take everything I say with a grain of salt, but LUB will try to find the lifetime that it doesn't know lifetime information, but it'll try to like create a type that is the lifetime LUB between two different types. So it'll produce a type that is shorter than both of the two lifetimes that are passed in, for example. Any more questions? Ooh. Okay. I guess we're almost, we're like an hour and 15 minutes in. I'm going to run really quickly through just kind of talking about all the different places that we use course many first. Non-library. So again, as I said before, we use course many in matches. We use course many in the return type. The ret coercion is what we call it, the return type of a function. We use, excuse me, we use coercion in the return type of an if-else statement. Or sorry, in kind of, you can think of an if-else statement as like a match, true, false. We use coercion in loops for the break tie, because you can break with a value, and that the tie that we want to break with should be the kind of the coercion LUB of all the different things that you break with. We use coercion in expression, or like an array expression. So all the different inputs to an array literal, that ideally we want to take the coercion LUB of all the different input types. And we use coercion in blocks, because blocks can also be broken from. And yeah. So yeah, blocks can also be broken from. And if that is only one, so if the block doesn't have a label, then it can't be broken from. And we just use course many, like it falls back to just using course many. If it has one arm, then it just uses course. Any questions about those specifically? I think those all should make sense why we use course many in all those cases. It's just ideally a lot of places we're trying to smush a bunch of different types that are unrelated together. Ideally we use course many to kind of make it as general as possible. Right. And then I'll jump one more kind of, let's look at all the different call sites to try course in the compiler. So try course is obviously used at cast sites, so for cast checks. And all these are different cast checks, and they all just use try course in different places because the code for casting is equally as kind of just like a bunch of different matches on tie kinds. This is course many itself. The main place that coercion's used in the type in here type check is this function called demand course diag. So I think last week I talked about a function called demand soup type or demand EQ type, and those are places they basically just, they're type checker functions where you pass in a function, or you pass in an expression, and you pass in an expectation, and an expectation, and it will make sure that they are equal, and it'll do some error reporting and a bunch of bookkeeping and stuff like that. So we have another demand function called demand course diag, and this is how most of the code in here type check does coercion wherever it needs to. And all it does is that calls try course, and it does some error reporting afterwards. Emit course suggestions is basically where all the useful suggestions happen in the compiler for calling toString on something and calling, did you mean to slice here and stuff like that. So then this is some error reporting code, and then right. So then the only other place that we call coercion manually and where we don't use demand coerce is when we're checking argument types in functions, because every argument to a function can be coerced implicitly. And that's why that box example that I think I had earlier didn't work, because we passed into a function and that caused it to be coerced. And the reason we don't use demand coerce in function argument checking is because we want to store that error for later, because we give better argument related errors. We want to be able to tell you that you inverted your arguments and you forgot an argument in the middle and stuff like that. So if we emitted a bunch of errors that have to do with coercions here, then they would either be redundant, or they're just, they'd just be redundant. Right. Any questions before I go on? No? Okay. So then just generally the places in here type check that we demand coerce are, I guess, let me just do all of them, are, for example, like, that's another helper function. Assignments, for example, struct fields. So struct fields can coerce their arguments. Index expressions. So the element to an index, like the thing inside of the square brackets, can be coerced. I don't know why that would ever be necessary. I guess so we get the implicit reborrowing when we pass a pointer into an index expression, because we can use pointers as index things, like for hash maps and stuff like that. Same thing with ASM. Okay, I don't know about ASM, but apparently we do some coercion and check ASM experts in overloaded binops. So we allow some types of coercions for built-in binary operations. So you can think of built-in binary operations as kind of expanding to function calls. So because function calls also allow, or kind of expanding to method calls is a better way of putting it. We allow some coercion on the right-hand side, which is useful for things like when you're trying to add a string in a stir, for example, like a reference to a stir. And then one last kind of, we can go up one more layer, is check expert coercible to type. We use the expectation, I think, of something like a repeat expression, which is, like 0, 10. We use expectation to provide coercion hints for repeat expressions, tuple inputs, the return, like the yield expression of a yield. I'm actually surprised that we use check expert coercible to tie for yield expressions, and we don't just use a coerce many like we do for return types, but that's just how it was implemented, I guess. Let's see. Obviously the return type of a function gets coerced. Binary operations, as I said before. More binary operations. And then this is on error reporting, I think. And then function initializers. So we allow coercions. Again, ties. Expert can be coerced into tie, doesn't need to be equal to tie. And then I think that might be it. Unless anyone wants me to talk about anything specifically, I think I covered most of the types of coercions that we have.
Could you just tell me what happens to the adjustments? Like, I know they're gonna get used by Mir, but like, where are they stored? Like, and
yeah. So we
stuff?
store adjustments in. Let me try to find somewhere that actually stores an adjustment somewhere. I think demand coerce stores an adjustment for. Oh no, check expert coercible to type, I think, stores a adjustment. There's somewhere we're handling the never adjustment. Here we go. No, that's diverging. This. So we store them in the type check results. The type check results is a big mega struct that stores all types of information that we infer during type check that we then want to reuse during typed here lowering and mirror building. So in here, there's an adjustments table. That's pattern adjustments. Here's the adjustments table. It's an item local map, so it's just a map between item local ID, which is just here ID, without an owner. So like a here ID identifies most things in here, and a here ID is made of a owner ID, which is the body that's contained inside of, and an item local ID. It's just a number that counts up from 0. Since we're type checking one thing at a time, we don't really care about the item local ID. I'm pretty sure, or we just care about the item local ID part. And right, so this is just a map between here ID and adjustments, a vec of adjustments, and this just stores the adjustments in order from like first applied to last applied. And then we later on, when we're lowering typed here expressions, we just map on that, and expand them into explicit operations in typed here, which then turn into explicit operations in mirror, if that makes sense.
Yeah, it does. Thanks.
Cool. Yeah, type check results also has a whole bunch of other stuff. Luckily, it actually is quite commented. I think the comments are actually a lot better than I thought they were going to be. And they're just storing a lot of different, types or a lot of different things. Unfortunately, the type check results they aren't typed well. Like, they're not taking advantage of the type system as well as I think they technically could. For example, like we just have node args, which these are the subs for anything that could have a turbofish on it. I'm pretty sure. And this is just a map from here ID to generic argsref, which is just a list of substitutions. There's nothing keeping you in, for example, like in diagnostics code, from trying to access this map at something that doesn't have a turbofish, like accessing it on like a literal, for example, like an I32 literal. Ideally, we would like have more granular IDs so that the type system will tell you like you're trying to access turbofish args for something that doesn't have turbofish. But I digress. This has nothing to do with coercion. But in general, yeah, all the information that isn't actually, all the information, including type information, gets stored in this type check results, and the type check results is it's the thing that is produced by type check and consumed by typed here building and lowering steps that happen after type check, and also consumed by things like lints. Lints also use the type check results in coordination with the here, stuff like that. So there's a lot of other helper methods on type check results to access all these and stuff like that. For example, there's node adjusted. There's X for type adjusted that will actually give you the post adjustment type of an expression, which is typically what you want. Typically what you want in a lint, for example, because it's like the type that something ends up being after applying all the adjustments to it, for example. So right, that's that. Anyone have any other questions? Otherwise, I think I'll wrap it up here. If y'all have any more questions, let me know. Ping me or whatever. I could talk about this far more at length, and right. So thanks for joining. I don't have the ownership of this recording, so I can't stop it, I don't think. Oh, I can. I can stop my share. Thanks for joining. I don't know if Santiago's around or not, but I think he can stop the recording.
You're the host. You should be able to.
Oh, right.
Actually, I can't stop.
Stop. Yes. There you go. Oh, stop.